Thank you very much.
Any other?
I think that we just anyway, we should do this second thing anyway, just in case. Yeah, let me just go back to my point. Yeah, that's good.
No.
I don't know what that is, but that's fine.
We'll check that.
Yeah, but this is fine.
Thank you. Please let us know.
Okay, thank you. What's your name?
Sweet.
Shri, thank you, Shri. Okay. So what kind of planning is it that I just did? So I have to have a plan to come and teach you guys, right? Is this the optimal plan that I did? Optimal plan would be starting about 2 minutes before and just running there and come. That's the optimal plan. What did I do? What is the characteristic of this plan? Yes? So give me a name, a character name for it. It's correct. That's true. But I mean, you do this, right? But and what is it? What the plan now? The one with my plan had a property. Is this working? Yes. Hello. You guys can hear me, right? So, what property does this plan have? No. Think of some good adjectives. What a better name for that? That's a very good, very good thing. Who's that? Who's that robot? What's your name? Okay, robust. Robust planning. That's what I did. Robust planning is never efficient in the sense of actually minimizing the amount of time I spend on the plan. Instead, it takes into account the possibility that the model of the world I have in my head is probably wrong. The model of the world that I should have in my head is this, what it's doing, wrong. And when you come here, things will be ready to work, wrong. But I have that model and I start, there's a possibility that model is wrong. So I took that into account and made a plan which would have been actually quite inefficient if everything worked. I would have had to stare at it. I would have been awkward silence. Who wants to talk to the lecturer before the actual class, right? Instead, thankfully, I got to stare at my computer. You got to stare at me trying to fit in the. By the way, this is called robust planning. It's one of the characteristics of plans that you might want to do, but let's get there. It's an interesting way of making lemonade with lemons, right? That's what we did just now. We basically had this problem, so we converted it into a teachable moment. Okay, so in case you are in the wrong class, this is CSE574, Planning and Learning, and this is for 2022. And I am Rao Kamabati, I'm the instructor. If you guys want, did you want to reduce the lights or anything? If this is okay, it's okay too. I'll just put down that, it's fine. I actually like to see people's faces. So the last time, so I actually, when I came a billion years back, before none of you were born, I made this one, right? CSE574 Planning and Learning. And I last time I taught it was 2008. 2008. Okay. So that's how I used to look in 2008. You see, there is a kind of a funny wig I'm wearing that apparently was hair. I no longer have it. And then, and that's how you guys were probably in 2008. I haven't taught that course after that. It has been taught by others, but I've decided I'll have some fun and teach this course at this time, which also means
that clearly I'm not just going to teach what I taught in 2008. Why? I mean, if I'm teaching classical physics, and I taught in 2008, can I teach 2008 classical physics now or not? Yes, of course, nothing has changed in physics. Unfortunately, we are in a rather sad, fast-moving field where you have to be on your Twitter even during the class to see if there is any point in actually trying to graduate. Right? So a lot of things have changed, a lot of things haven't changed. And so what I am going to do is basically try to take all those things that have changed into consideration in trying to get you into this course. So anyway, so I'm the instructor, Ram Body. Most of you, is there anybody here who didn't get a Piazza invite? Okay, so unless you haven't, added as of 10 o'clock in the morning, you probably didn't get it. If you didn't add until 10 o'clock in the morning, then you didn't get it. So you will get it like today when I go back. But I think most of you actually got this Piazza notification. And so that would be our main forum for talking. Okay, everything on that. And some of you, one of the pleasures of this class is there's a bunch of people whose faces I know. Actually, I just taught them in fall of 2021. And they know how much we use Piazza. And it's like, we wind up using a lot of, I actually pay for it, by the way, because the ASU no longer pays for Piazza. And I can leave it in the free mode, but then the Piazza will ask you. And you might think that I'm asking you to donate to me. It should be good, but I won't get that money. So I will actually pay for it. So that I can use that. I love the interface. It's actually very nice. I don't know whether I decided not to use it. So we'll use Piazza. And most of the communication is with Class Piazza. And then you can use the private messages so that only instructor sees it. Some of you have already figured that out, right? Basically, I asked MS students to tell me if they have done intro to AI or not, and where have done, etc. Several of you already gotten back to me, already okayed it, etc. So you could do that. And then if there are things that you are unrelated to the class that you want to talk to me about, send me a mail, at ravate@ac.edu. I will tell you what my office hours are, but in this day and age, we are like constantly in contact. If you really want to, you can actually send me an email, you can talk on that. There's going to be an official team and grader, etc., but there aren't anybody who's actually qualified. So who they gave, I didn't want to teach the TA how to grade, so it makes no sense to me. So right now we are still looking for a TA. We'll figure that out. But then, as you can see, there's some people showed up to actually record me. By the way, that's another level of robustness. Okay, so I got behind you, lo and behold, a camcorder. That you used to have, million years back. And I got that so that everything fails. That will work. And you can see that robust plans are never efficient. They just, what they do is they minimize regrets. Regret at the end of the class that I'm so sad that they don't get to see my face and I'm not, forever life. Okay, so anyway, that basically my PhD students are here and they will try to chip in as unofficial TAs, and then actually they'll also play an important role. I'll talk to you about in a minute. Okay, so before I go forward from now, by the way, this is a very long class. Yes, you didn't realize, and I can talk forever. I actually got this before caffeine drink. So normally itself I can talk long, and with triple caffeine drink, who knows when I can stop. But we will actually take a break. This is 1:30, so maybe around 2:30 time frame, we'll take I don't know, I think 10 or 15 minutes. Has anybody done these 3-hour classes before? Yeah. How much time does it give you normally? I'm sure he's going to say 2 hours. Go ahead. 10 minutes. Okay, we'll do 10. Yeah, we'll do something like 10 minutes, and then so that you can stretch your leg, go, buy a breaker and so on. Okay, plus or minus, so that there is a reasonable place to stop. Okay, that's what we're going to do. And so before the break, I want to give you an overview of what the topics are. Okay, it's actually quite useful to understand this. May not make too much sense right now. It makes huge sense if you come back to it during the semester as we're doing things. Why are we doing these things? Okay. And so we actually will get reasonably deep in terms of not specifically technical formulas, etc., but different kinds of planning. For example, the robustness stuff will show up in a minute. Okay. And also what are the kinds of issues that we'll be talking about. And then during this, please stop me, ask questions, etc. as usual. So before I go to there, are there any? So I will tell you that we haven't figured out what the grading criteria is, partly because I don't really know how many of you are going to hang around. And I really, as I sent in the message, it was actually, I think it's nicely falling as it's more falling. Leave after the break or something. Basically, people who are doing it because they want to have a course, it's a bad news. This is not the kind of thing. Ask these four guys who took the class. This is not what you do for a course. Okay. And I know that master's students have a pretty straightforward plan, preparing for the internship coding interviews, doing the coding interviews, getting the internship, getting the job and leaving, which is completely fine. It's a great optimal plan. It doesn't have too much of a space for this sort of a course. So you should do it. I mean, you should know what your reward metric is and work for that. Okay. So, it's probably very useful for PhD students and also be useful for pretty much anybody who wants to kind of connect all sorts of dots in the way, AI is going in the context of that. Okay. And it's not going to be in your coding, unfortunately. So that's why I think I should just tell you that. Are there any questions before I go forward? Okay, so what is planning? This is my definition. It's a reasonable definition, I think. Planning is deciding a course of action before executing. Do you understand what I'm saying? If you just do something and say, I did it by plan, then you are deluding yourself. You have to have had the plan beforehand, before you start executing. You may change the plan, but you had a plan. There's a beautiful quote by, I believe, one of these great generals. I'll try to send it, on the other one, but it goes something like, in war, it is critical that you have a plan. It's not important that you follow it. It's critical that you have a plan. Because the very exercise of making a plan makes you at least think about what the environment is, what the problem is there a possibility of meeting the goals, etc., etc. Okay. So planning really is about deciding the course of action before executing it, which also means that there are like two different ways people think of plans. In normal life, you tend to assume, believe it or not, deterministic world. By the way, this is another thing I assume that all of you have taken into AI. I will be using terminology about health, environment, etc., etc. If you are really stuck, ask me. But in general, I'm assuming that some of these concepts are like the second time you are hearing, so that you can actually go into other things. Okay. So planning is deciding. So a plan is either a generalized sequence of actions. So typically you think of a plan as I first do this, then I do this, then I do that, then I do that. That's a plan. I said generalized sequence because it doesn't have to be a direct, totally ordered plan. It can be, I do this, and then in parallel, I do this bunch of actions and this bunch of actions, and all of them got done, then I will start doing other. So it can be a partially ordered sequence of actions. You see, understand? Let's see if I can actually write this. Yeah. So a line plan would be like this, where the circles are the actions. Okay, can you guys see that at all? Okay, okay, this one. Oh, okay, that's possible. Could be that happens. Okay. Oh, this is not good, but yeah, it doesn't actually give me yellow. Believe it or not. Green is better. Okay, yeah. Is this better? Thank you. That's um, a line plan. I can have something like this. That is a partially ordered sequence of things, right? So if this building was built a couple of years back, maybe 3-4 years back. So they had a project plan for building this building. The project plan won't just be do this action and this action, because there are multiple agents, a huge number of people involved in building this. The electricians are doing certain things in parallel with somebody else doing certain other things. They should make sure that these things can be done in parallel, and then all those things are done before some flooring, carpeting is done. Because after you put the carpeting, if you want to do wiring, then like put on, under the floor wiring, that's bad news. You'll be wasting your time. So that would be called a project plan. And the project plan, typically, project plans are typically partially ordered. Okay. Now that is up to the generalized sequence part, but it can also be even more generally. It is a policy. A plan and policy are used synonymously, but a policy really is, if I know the state I am in, I should know what action should I do in that state. You understand what I'm saying? So if I know what the state I'm in, I'll do the action. Then I'll see what my next state is. Then I'll do the action in that. Then I'll do the next state in this. I'll do the action. Interestingly, if I have this kind of a plan, it is a policy. And if I realize that this is a policy, it's a policy which essentially says you don't need to look at the state. Right? Irrespective of what the state is, do the next action, next action, next action, next action. Do you understand what I'm saying? So it's like, and so in fact, this state, the line plans are most useful in worlds which are sort of fully observable and everything goes according to your plan, so that you can just do things with your eyes closed and you will reach there. You've seen these, what do I think called the Rubik's Cube guys, who basically just close their eyes and start doing things and it will be done. So because they've essentially converted normal Rubik's Cube guys like you and me, will look at the colors, do something, start crying, do something more, start some more crying and give up. That's what is called a full policy, where you look at the state and say, how the heck did I start getting into this? I should be doing something more useful in my life. Okay. Whereas you could do like a line plan where somebody might have said, if I start from here, after these, then basically. You understand what I'm saying? So interestingly, sometimes you either the world is not observable. Remember, there was this other aspect. I said deterministic part, but I also can talk about observability, partially observable, fully observable. And the observability, if the world is not at all observable, you can still sometimes do planning. Where if the world is not observable, then you assume that it's one of the many, many possible states it will be in. I'll just keep doing my stuff. And mentally, you will realize that it's probably in one of the many, many states. I do this action. Now there will be fewer states, hopefully, or maybe larger number of states. But I do all these actions. In my head, I'm seeing the number of states coming down. Bomb in the toilet. Some of you know about this. Okay, so you go in the break to the toilet, right? There is a bomb sticking away. They don't call 911. It turns out that essentially, no, there's a package and it's sticking away. It may have bomb in it, it may not have bomb. You try to touch it and open it, the damn thing blows on your face. And so you will miss the second half. Here is a fun shot. Okay, right? And however, it turns out that you all know that whatever is bad thing in life, you can always put it in the toilet and flush it. It's not, it's somebody else's problem. It will blow up somewhere else. Will you succeed solving, saving yourself? You have that access. Of course, your friends will say, I want to see whether there is a bomb or not, they're dead. You would say, I always flush. I don't care, I just flush. You win. You took a word which is actually not even observable and converted into, basically an unobservable word, and you still succeeded the plan, doing the plan. Because essentially, it turns out that irrespective of what was there before, after the flush, the bomb is gone. Okay. So many cases, actually, policies can be line plans. In many cases, policies also can be actual state action matters. Because you have eyes, you should look at it. If you call your doctor and say, doctor, and they say, take your aspirin and go to sleep. You have used conformant. So I don't waste my time. Just take the aspirin and go to sleep. If on the other hand, say, come, I do this test, do that test, charge you some more, charge you some more, and then give you aspirin, they are essentially doing a policy. It's basically looking at the state based on the test result and figuring out. Okay, so plans can be either generalized sequences or more generally policies themselves. And it's kind of important. And both types of things would be useful to have in mind. And so computational. So, are there any questions on that part? First of all, okay. So computational models of planning. So what we are interested in this course is how to make plans. That's what we are interested in. You kind of have a sense of what plans are. Now what we are interested in is how to make them. Well, for that, you usually have a computational model of how to generate plans. What are the algorithms? What sort of methodology are you using? Now it turns out that's the fun part where computational models for planning differ wildly in all sorts of ways based on certain assumptions that you can make on the problem or the certain kinds of requirements you have on the plan, etc., etc. And this actually, the next slide onwards, it's like a 4-part thing which continues, basically giving you the dimensions of variation that I could think of this morning. There may be more dimensions, but certainly these are like some of the important dimensions. And you'll see as you're talking about this, all sorts of random things that you didn't think would be connected to planning will start showing up, such as reinforcement, such as large language models, such as motion planning. They're all basically, with respect to this particular definition, they all fall under the rubric, but then special cases can have better algorithms. Okay. Now, let's see. Yeah. So, computational models for planning differ based on, there are many, many dimensions. Dimension 1 that I'm working on. Let's see. Yeah. Dimensions. This is the first dimension that I'm going to look at. What guarantees are given on the plan? Okay, I need to change this. Okay, what guarantees are given on the plan? And there your robustness already is coming. I made a plan. Is it a good plan? How are you going to measure whether my plan is a good plan or not for this problem? One is validity. is this plan likely to work even given your model of the world? Do you understand what I'm saying? Right? So if you have a model of the world, so for example, if you say now, during the break, you want to get coffee, you made a plan saying, then I'll just, flex my hands and fly in the air and get to Starbucks. That's a plan. It's a stupid plan unless you've fallen on your head on the way to the class. Because even according to your model of the world, you don't have the flying abilities. So understand what I'm saying? So is it valid with respect to your own model? Otherwise, it's delirious thinking. So you might come up with a better plan, such as I will walk and get the coffee. You may not actually succeed in that. While walking, you may get run over by a bus. I'm trying, it's kind of unfortunate how much I'm trying to reduce the number of people in the class, but or you go to the coffee place, there's way too long a line. I don't get to laugh at you because you made a valid plan with respect to your model. The world changed. The world was dynamic. It have changed. Like, for example, you go and Starbucks had a fire, they close. That's not validity. That's still, so if you can actually, if the plan were to work within your model, it's considered valid. It's considered valid. You guys understand that? Right? The invalid plan is the one where you said, I'll then, fly and get my car. Because even it won't work. Why the heck were you making that plan? Okay. So validity, optimality. With respect to your model, is this the best plan? According to some metric. For example, it uses the least amount of resources. It takes the least amount of time. It uses the least number of actions. They're all different metrics. Anytime I say optimality, you have to say with respect to what? What's your metric? In general, for plans, the reasonable thing is things like, the reasonable metrics are amount of time you take for executing the plan. By the way, route plans are things that right? Google Maps makes your route plan. Yeah, are Google Maps plans optimal? They suck, but we use them. But even if you are thinking of whether or not they are optimal, how are we supposed to check whether they're optimal or not? You should ask yourself, is this the shortest plan? In fact, Google tells you, every once in a while, that Google woman provides something and say, you're still on the fastest route, despite the fact that everybody in front of you has stopped and their cars on the fire. This is the best route because according to its model, according to exactly, the model that is actually capturing. In fact, in the case of route maps, one of the nice things is the map of the world that it keeps is dynamic. It's getting information, additional information from the cell phones of the various people about the traffic. But even in the case of route plans, there are two different optimization metrics. The length of the distance, length of the path, which is basically what you would care if you're an Uber driver, right? How many miles have I driven, and the time. You see what I'm saying? And once in a while, when you talk about optimization in this particular case, one of the issues that happens is in the case of multi-objective optimization, that means there are multiple ways in which you can optimize the plan, it becomes hard to tell which plan is better. You understand what I'm saying? So take, let's say, a flight example. So I'm going to go to San Francisco. Here is one particular sequence of flights which take me from from here to Tucson to Los Angeles, Los Angeles to Las Vegas after a bit of running, and then I'll be another airport, and then I go to San Francisco. That's $25. Right? And then there is another one which directly goes to San Francisco. That's $26. Which is better? Let's assume, for the heck of it, that all that matters is the time that you spent on the travel. Although actually things like whether the seats are cushiony and whether the air hostess and the airline crew are particularly mad at you on that day, those things matter too for your utility. But let's assume that all that matters is the time of the travel and the price in the case of airline travel. And let's assume that the circuitous one takes 15 hours and gets done in 25 hours. And the straight shot one takes 2.5 hours and gets done in 26 hours. That's the price of it. Which is better? Who said second? You should not be a grad student. You have an extra dollar to spare that. I know, but how did you decide? There are people in this world where $1 is it's not extra, it's not available for you. You can't make up their mind. I mean, just as you said, it is definitely second. If I said instead of 26, I said 2600. And if you still say yes, then I really, really want to get out of that. Why is the grad? You understand what I'm saying? So the point is, everybody has different preferences. And there are different ways. This guy apparently says, oh, $1. For other people, I don't have that kind of dollar. I'm not made of money. I'm going to take this forward. Okay. In general, one of the interesting things about these kind of multi-objective optimization problems is, let's say this is the time and this is the price. You guys see that? Okay. Now each plan will be a point. For each plan, there is a time and a price. Right? And if you actually make it in such a way that the higher price is worse and higher time is worse, that's what you care about. So it's actually reasonable to say time and price. Okay, so then this particular, there is a kind of a curve here. Does anybody know what the name of that curve is? Pareto Franklin. You heard some new word. Okay, so it's called Pareto. Or a Pareto curve. All you can say, if you don't know anything more about people, you have to give them the entire Pareto frontier. You say, you pick the plan. This guy wants me to just say, why should you care about extra dollar? No, you shouldn't do that. You should give me the option. You see what I'm saying? Otherwise, you can always take a multi-objective optimization problem and then multiply the time alpha times price plus 1 minus alpha times cost, or alpha times time plus beta times cost, and convert it into some number of apples plus some number of oranges equal to some number of fruits kind of image. Then it becomes a single objective problem, and then you can optimize. Right? In planning, actually, depending on whether they're doing multi-objective optimization or single objective optimization, the algorithms would be quite different. And the reason I bring this up in much of the first part of the class is, if you read people papers on planning, they don't look at all like they're talking about the same problem. And we're just starting at the beginning right now. By the time we go in the 4 of these slides, you realize there's so many differences that 2 different planning problem papers may not look at all like they share anything. And so it's very easy to think there's nothing common. But the hope is the syncretic view. That's another word I just love. A syncretic view that you'll get in this course will make you realize that they're all essentially solving the same problem. And that you can actually, if you are essentially rediscovering the wheel, you are rediscovering the wheel. It doesn't matter you're rediscovering a wheel in Mesa and it only existed in KP before. You understand what I'm saying? There may be an arbitrage opportunity because Mesa people don't know each other. But intellectually speaking, the wheel has been discovered. And you shouldn't be rediscovering. You understand? Okay. So that's about the multi-objective optimization part, about the optimality. So best plan according to some metric. It can be the shortest path, fewest actions, lowest cost, highest expected value, and also, as I said, multi-objective optimization multi. And then finally, robustness. That could be a very important characteristic of the plan. That I already told you about it, so I won't say anything more. In general, these two things, validity and optimality, assume that your model is actually correct. And they're trying to make the plan the best with respect to that model. Robustness realizes that your model can be incorrect. It's probably one of many possible models for this problem that you could consider. And then you have to essentially see for any plan, its cost depends on what ends up being the real model of the world. There's actually a spread. That's what I was doing when I basically came too early to the class, because I didn't quite know which model I would be in. Would be in a model where ASU's computers work right, or would be a model where nothing works. And I kind of, came up with a reasonable value, what I called was a valid plan. Again, when you're taking robustness into account, validity is a harder thing to define, because if you didn't even consider a particular type of world occurring, then you will never actually have come up with, a plan that is that. Okay. In fact, robustness is connected to another idea that we'll talk about in maybe our third slide, or something called open worlds, which is like a huge thing in AI right now in general. Because what is an open world? It's a world, basically, you have some model of the world, but you're not sure that that's the right model. And there are many, many things that the world might be doing. And you just have to figure out what are the likely things that can happen. And their robustness becomes very important. Okay. That's the first dimension. Any questions on this? You can kind of already see how, if I start giving like a planning algorithm, the one for validity would not care about optimality. The one for optimality from the intro, 471 point of view, optimality, if you have a single objective, you would use A star search if it's a deterministic one. Right? And that's how you get the optimality. Okay. And if it is multi-objective, then you need to actually compute the Pareto frontier. And then it becomes actually a more interesting thing. Since I'm talking about this, imagine you're a travel agent and somebody says, give me some options, and then you give the entire dense set of Pareto options. What is this thing that the one that Orbit's people, Orbit's used to use this particular service? You know what I'm talking about. Google actually uses it too. It gives almost the entire Pareto frontier of all the slides. Which one? Slide metrics, exactly. Slide metrics. What is slide metrics doing? It's basically only useful for grad students who want to save $1. Right? And basically don't have any other constraints on their time. So you stare at all of them and then pick one. Expedia, etc., then they say, oh, take this, or this. How did they decide? He said, just take one. And I yelled at him. Expedia says, take these 4. One of them is the best. The difference is Expedia is looking at the Pareto frontier, sampling reasonable points on the Pareto frontier and saying that's reasonable. Why is it reasonable? Because the plans are being presented to the human in the loop. If you give matrices for human who are not grad students, and grad students are like barely human, right? And engineering grad students, particularly barely human, right? They would say, what the heck am I supposed to do with this information? It's information overload, man. Just tell me something. So sometimes in the case of Pareto frontier, one of the interesting questions becomes how to get K plans that differ enough from each other that the user can look at them and pick what they want. Now, I never actually told you that there was a use. Before it looked as if it was just a single agent which is making the plan and doing it. But here it could be possible that these plans are being made for a human to execute. Travel plans certainly are made for humans. Robots don't make travel plans and actually go fly. Right? And so in that case, you have to take into consideration the human frame. Okay, and we will actually get into that too. Okay. So the next one that I want to look at is what input is assumed. You didn't ask this question. I mean, it's like, each of them are so many different variations that by the time you will actually forget, how many dimensions you will take. First, I just said, make a plan. Yeah, I'll make a plan. Then I said, make a plan. How good is the plan? And these are all the first issues. Then I'm asking, how did you know how to make a plan? What's your input? Now, if as soon as I said make a plan, you start making a plan, and you don't care about what goals I have, you don't care about what the world is, how does it happen? Right? So it becomes an issue of what input is assumed. Typically, there are two kinds of inputs that a planning agent has to assume. One is the world model, the dynamics of the world. You do an action in a state, what happens? You see what I'm saying? That's the dynamics model. This has also been called the world model. And, world models have been used forever in AI. In fact, if you took intro to AI, A-star search uses world model. But it's become like a big deal now in AI, the new AI, because some people haven't ever used world models and they're saying, what we need is world models. Okay. Anyway, so world model is important if you want to do plans. Okay. And the models that will give you the dynamics of the world, roughly what is the expected result of doing an action in a state. If it's a deterministic world, you do this action, you get this, what state you have. If it is a stochastic world, you do this action, you know which set of states can occur and with what probabilities. Those are both world models. The deterministic world model, one is a stochastic world model. You see what I'm saying? That's one piece of information you need. The other is goals. What is the plan trying to achieve? You kind of assumed that when I said my plan was robust, I say you should ask, what was your goal? Well, my goal was to start the class on time. That was my goal. See what I'm saying? So depending on the goal, depending on what the plan is trying to achieve, the best plan would be very different. Okay. So the goals would be objectives. It could be like I have to start the class in a certain time. That's an objective. Okay. Preferences. It actually turned out that I put on this silly hat and I started walking because the best way to come, it turns out, without having to see anybody at all, from Brickyard to here, is walk through that middle, through near the mosque and so on. Turns out, sun just keeps falling. It's kind of hot. So, I had this grad student, Sriram, he cut, basically he shaved off his head and he started always walking on the western side in the afternoons because the western side has more shade. I'm giving you useful information. When you go back, you can walk on that side. Actually, walking on that side is costlier because I have to walk longer. Because I have to go like that, go like that, come like this. But I have this preference of keeping my head cool. Because otherwise I'll be even more angry at you than probably I am already. Right? So that's a side preference in addition to starting the class on time. Some other people may not. Some of the young people say, wow, it's great. And I have my scooter, I just zip through in the middle. So it's just your preference, that's fine. Okay. Preferences and side constraints that I have that are not environment's constraints. Those are my interests, the agent's interests. Those are the two things that you need to make it. Can you think of anything else that might be needed to make a plan? I don't know, maybe I forgot some other things. What? It's a preference. Right? It is actually a preference. Interesting. It's a lovely point, by the way. Safety is a preference. And by the way, one other thing is these goals, objectives, all these things, they are generally f of trajectory of states. It's a function of the trajectory of states that you go through. Notice that way, my preference of going through the shade is nicely captured. That way, it also captures me being in the classroom because the trajectory must end in the classroom. And it should go through shaded region. And this guy says it should avoid walking in the middle of the road and getting hit by cars. That's his preference. So in general, preferences can be thought of as, those of you who remember from the intro to AI, performance metrics are f of the state trajectory. It's always that way. Yes. What? Yes, so that basically is a reasonable question. I mean, should I have initial state or not? You could have an initial state, actually in certain class of problems. It's actually a good point to have. So a special case is initial state. It could, I mean, what I'm saying, so the initial state can be either part of the world model or part of the preferences, really. But it's really special case because many a time you might have a policy which tells you whichever state I am in, how to check it. Okay, but in fact, when we look at the deterministic planning problems, which is what we'll do first, in fact, planning problem is I, G, O. I is the initial state, G is the goal state, O is the set of operators or actions that you get to do. So in that case, yes, initial state is. The expectation is it's sort of combined, captured in both, but sometimes you can ask for the details. Yes. Yes, so where are the capabilities of the user in this? What? I'm sorry, somebody said? Exactly, but where is it? Did you get one of those? Exactly. Because the dynamics of the world actually captures what world does if you don't do anything. First thing, not doing anything is a deliberate action. You understand what I'm saying? Not doing anything is a deliberate action. For people who can do things, not doing anything is a deliberate action. Okay, so dynamics of the world include how the world will evolve from state to state to state if you don't do anything, and how it will evolve if you do a certain action. If the world is moving, if you don't do anything to it, then it is called what kind of a world? What kind of an environment? There's a name for it. Dynamic. A dynamic world, if you close your eyes, it's still moving. A static world, if you close your eyes, everybody stops until you make up your mind as to what the plan. Anything else anybody wanted to bring up that's not more captured there? Again, notice that it's a fairly high level. I didn't put on any formulas, etc. We will do that. But I cannot stress how important it is to come back to these slides during the semester to see how things are connected. Why, what is the difference between this planning problem with our planning? They're all saying they're planning, but they have very different terminologies, very different formalism. But the underlying problem is the same. Yes.
Where do we capture the entropy of the world? That the dynamics of
Basically, that's dynamics. I mean, entropy in the sense how much the world is changing. That's just part of the dynamic. And the robustness is a preference. Robustness is a preference. Yes, so you have safety as your preference, and the safety is higher in certain ways. The world evolves and lower in others.
where do we capture our set of resources?
That's a good point. Again, it turns out that the dynamics of the world also captures the kinds of actions that we can do. But it is useful to differentiate resources because in one of the things we will say that the difference between planning and scheduling is an important difference. People do scheduling and some people do planning, and when people doing planning, the planning is more general than scheduling. People doing scheduling, say planning, people are lazy. They actually have a plan that can't actually be executed because it expects resources that are not available. For example, remember your plan about flying to the Starbucks, right? You are delirious if there was no such resource. If on the other hand, you did have, you're flying whatever wings or something that Uber is, you can buy them or you can pick them up, except you didn't bring money to get one of those resources, then the plan would have worked if the resource was available.
So wouldn't that also come under your priority, your resources?
No. Again, these are different dimensions. This is how good is the plan. This is what is differentiated. Yeah, because validity, so in the sense that if the plan isn't working, it could be maybe not working because you essentially completely ignored the model, or because the resource you expected for it to be available to you is not available on that particular day. Okay. Okay. Let's see what happens. So okay. So the second part is computational models. I'm continuing this. Computational models for planning differ based on how the models are taken. And I talked about the goals and the dynamics. Then the other part is how the models are taken in. So the previous one, just to give you a sense, what input is assumed? The input assumed is dynamics and the objectives, the goals. Okay. Now the next one is how is it taken in? You understand what I'm saying? How is it taken in? It's actually very interesting that the most general model would be that the planning problem is specified along with the world model and the goals. And a part of the world model are goal to be initial state. So initial state, goal state, and actions. That would be the most complete specification of the planning model. So the domain independent planning assumes that the models are given explicitly. They're actually given to every time there's a new problem, you would say, this is the initial state, this is the goal state, these are the actions. It's called domain independent because if the planner is working, it should be able to work for whatever is initial state, whatever is the goal state, whatever is out. You see what I'm saying? The next thing, just give me a second. So the next thing is domain specific planning. If I said, what's your plan? And you right away started asking what the plan is. And I said, how the heck can you start? Well, it's because you compiled that always asks this particular goal. And the world is always this model. I'm sick and tired of acting as if it's freshly new. So I'll compile it into my reasoning. Time for system 1 and system 2. People know system 1 and system 2. These don't exist, but it's like a big deal. Talk about system 1 and system 2 to impress people in the audience. Okay. So basically, there is a psychological model of the human reasoning, which says that we could think of human mind as having the system 1 and system 2. System 1 is reflex. System 2 is deliberate. One of the interesting things is the word compilation means there was a source code that got compiled. So something that started in system 2, planning is like a classical system 2 problem. But if you do that plan lots of times, then at some point of time you have compiled that into a policy that you just started using that. Then it becomes a system 1 degree. So some variation of that in between those two is basically, if you don't ask for that domain model, then it becomes If you don't ask for the domain model or the goal or the initial state, then you get the domain state. Because you are assuming before you even say, that's what you want. You get this? It's kind of strange. The domain specific you would think will need more input than domain independent. But actually, if you think a second, you realize that domain independent needs more input because it's supposed to work everywhere. So before it starts working, you should tell it what it should work on. Whereas the one trick pony, if you just do that trick, irrespective of where you are. Domain specific planners are one trick pony. Sometimes the tricks are good, sometimes they're good. Okay, that's domain specific. Okay, this is a good place. After this, we can stop and then come back. Going slower than I expected, but not abnormal. In both domain specific and domain independent, I am talking as if somebody is giving the model. Somebody being like a programmer, or somebody who is like a user of the domain, knows something about the domain, and they'll say, these are the actions, this is my goal, this is my initial. Okay. You could say that I don't want anybody to give me anything. I want to learn from scratch. Or there's nobody to give me. I have to learn from scratch. In which case, the learning basically can be applied to either the domain dynamics or the goals or both. You understand what I'm saying? Now, before we go forward, one of the useful things to understand is the way, what are you learning from? What are you learning from? The simplest and the most reasonable thing to say is the agent learns from its own experience in the past. So it hung around doing actions in the world, figured out what they seem to be doing, and built a world model in its head. With respect to it, it's doing that. Okay? That idea is basically reinforcement learning. To give the model, it's planning. I have to learn the model too, it's reinforcement learning. The real world is somewhere in between. I'll give you some aspects of the model, and you shouldn't dismiss me when I'm ready to give you aspects of the model. And then you have to learn some other aspects of the model. Okay. So either agents, so if you're learning it from the agent experience, and one of the other points to make here is what are you learning? As I said, you could learn, the most simple thing is learn the dynamics and learn the goal, then you will be back in the previous thing, right? I'm sorry. Yeah. So if I can learn the model of the dynamics and the goal, then I'll be back into my old subject. That's a very reasonable thing to do. Okay. That very reasonable thing to do is called model-based reinforcement learning. That's what I'm saying. So rather than, so basically the learner is just learning the model of the dynamics, model of the goals, and using them to generate plans. That's called model-based reinforcement. And model-based reinforcement learning is like so damn close to planning. Right? Because if you stop learning for a while, you have a model, then you apply it to, you use your planning algorithm to make a plan. This is the connection between reinforcement learning and planning. They are like extremely close. Ideas flow on both sides, but when people come into the field from one direction, most likely these days in reinforcement learning, they won't know anything about what was done from the planning. Okay. So the most obvious idea is model-based, learn the world model. Or the other is if you're learning anyway, why learn the intermediate part? What do you want to learn? Plan. I just learn the plan. You understand what I'm saying? That would be called model-free reinforcement. Okay. Now, how many of you have heard model-based versus model-free before coming to this? Okay. Now tell me, is there a connection between model-based, model-free, and anything else on that slide that you already seen?
It feels like model free feels like the domain independent planning, and model based feels like a domain specific planning, in the sense that what if you just learning your policy doesn't, you can apply it to multiple things, the same model.
Okay. I mean, if only I can remove my mask, I can smile at you. I will say, you came so damn close and made a mistake, but anyway, that's a different story. So I'm laughing behind. You give, and so actually, by the way, those of you who have taken my notes, no, I don't know. I asked true or false and asked for justification. And your justification is right on the point. And the true false is
I saw that.
And in the exam, you have got points. Whereas people who pick the true false correctly by passing their lucky coin and give the wrong explanation would get 0 points. Okay. So people understand exactly what he said and just reverse the polarity of his conclusion. Then you're right. Model based is essentially learning the goals and the domain dynamics. And so it can have any goals, any domain dynamics. If the goals change, it has new goals. So it's like domain independent plan. Model free is a single damn policy. You think AlphaGo, which you are so damn impressed, right? Because it's a model free learner. You say, oh, we hear that you are like a great deep mind program. Can you tell me how to go from my home to Safeway? But you are the Go champion of the world. You understand what I'm saying? Because it's model free. It's extremely important to understand that AlphaGo is domain specific. It only works in one world. It only works for one goal. What if I wanted to, I don't even know what goal is. Like imagine it's alpha chess. Imagine my interest is to kind of put my pieces along with your pieces such that we can spell happy. That's the reason I'm playing chess. You think Deep Blue will help me with that? No. They'll just make me win or lose and be done with it. But how dare Deep Blue tell me what I should feel about chess? This is my goal. I want to, make happy with the pieces. Deep Blue won't help you. Can you? Of course you can. Even those of you who are very bad chess players, in the sense you basically Gary Kasparov would just laugh at you and probably won't even bother laughing at you. Have a general understanding of the board, general understanding of the actions, and now you have been given a new board. You can actually make it. Generality. Domain. You guys hear about this. I know many of you are coming here just because on the street everything is about certain types of neural network-based learning. You know certain things more, not other things. Okay. You sometimes hear about generality, right? The most important generality is being domain independent, task independent. Yeah.
There is a new policy that gives the same level of optimization. So when you say that it's model free, if there is a true
No. So model free, yeah, no. So model free just learns the policy.
The series of this one.
So if what you're getting is if you're in this case, do this action or do this other action, right away, as the end of learning, then it's a model. If the end of learning is a model, which then has to be used to compute the policy, then it's model based. However, those of you who know reinforcement learning know that these things can be interleaved so finely that model from the iteration I-1 becomes used for computing the policy, which then is used to compute the model from I+1 time. But the advantage in model-based and model-based is after solving the problem, you still have the world model. So if the goal changes, you don't have to start from scratch. You can keep the world model and change, use the new goal. You understand what I'm saying?
So, Professor, would it be okay to say that the model free is quite dependent on the model base sometimes?
No, model free doesn't remember model at all. And actually, just to give you again, we're going into fairly technical distinctions in the reinforcement learning. And again, as I said, the people for whom this kind of discussion sort of makes sense have the right kind of intro to AI background. And I want to take you from there to the next level. The people for whom whatever I'm saying is what I'm saying, you should probably do it to the AI. I've spent a ton of time making that. Okay. So in the context that I have here, model free is basically essentially just learning the policy directly. And so if the goal changes, model free doesn't know what to do. It doesn't know how the model works. In some cases, you can do either model based or model free. In other tasks, only model free is doable. Intro to AI folks, please tell me which ones. Give me a task where model based is not even a doable. No, my canonical example is swimming. You don't know, you have no model of swimming. You fall in and then there's no what's happening. Sometimes models are, so the point is the model free versus model based. Here is the problem. You're going through the intermediate stage of model to go to the solution. That's model based. If you go directly from here to here, this is model free. If you go through the model, it's good because you can use the model some other time. But what if this model is extremely painfully large? Okay. In fact, one of the interesting things, this is actually a point where we start talking slightly differently now than we would have done like 10 years back. When people said large models, it was always this question of large by human, measures. You could actually have AlphaGo 2 model based Go learn. And that model will be incredibly complex. It won't make sense to you, the humans, but it is actually using it, as a model based. And whether or not model based will be better than model free depends on whether the models essentially become just too big that going through this intermediate stage is not useful at all. A very interesting analogy is if you think of supervised learning. Again, I'm assuming that you know this because you should, right? You give an example. I want the label for the example. Right? And the training data is a whole bunch of examples and their labels. And you're trying to figure out, given a new example, what its label. To go directly from examples, the training data to directly, the labeling the new example, you're doing non-parametric learning. If on the other hand, you look at the example and you say hypothesis, and then hypothesis to label. That's model based. Understand what I'm saying? And so there are all these connections across ideas, model free versus model based is connected non-parametric versus parametric learning. Okay, should we take a 10-minute break now and we can come back and continue? Okay. Oh, actually, wait, just one second. Oh yeah, okay. I'll let you go because I still have to do these to remind me. Okay, take your time.
Yeah, so in the same example, the reason the model is
Okay. Yeah. So the agent, when it is learning, it can learn from its own experience, which is the classical reinforcement learning. Okay. And people say reinforcement learning, the way organisms learn basically is by doing things in the environment and getting the reward signal and then trying to figure out what actions are being. Many of those organisms die. Other organisms which are looking at them say, "Oh, that's not a good thing to do." They might learn. Reinforcement learning is not safe for you. You understand what I'm saying? What people do when they say reinforcement learning is they will actually, instead of having experience, they will provide the world model as a simulator. How many of you know flight simulators? Those of you who did flights, Grand Theft Auto. After doing Grand Theft Auto, you should just say, it's a plane as a car, and you go into the car, you're dead. Because in the Grand Theft Auto, when you're dead, you get back. Right? And it's just basically a new episode. Whereas, unless you believe in the huge, reincarnation or something, you're dead, you're dead. So instead, what people say is when they talk about reinforcement learning, they're talking about reinforcement learning with respect to a simulator. A simulator is a world model that somebody built. What's the difference between that guy giving you the model versus giving you the simulator? One is probably a piece of code. The other is probably some sort of a formal language. You understand that? Okay. So RL, typically, it's very important to understand that simulators in RL are there are no simulators in pure RL. That's what I did say. There are no simulators in pure RL. If you're using simulator, if you have a simulator, it is a given model. You can pat yourself saying, I'm just doing planning data. Yeah, of course not. I spent time writing flight simulator for you. Understand what I'm saying? It's extremely important to understand that. If the simulator is available, you can use it. Don't trick yourself. That's basically learning from experience. It is learning from experience with a piece of code. If you die in the piece of code, you still don't die. Except, I guess, in Inception, where they say that you die in the dreams, you can actually die sometimes. I was very worried because I get very visceral dreams. And that's kind of what it is. But anyway, okay, it's important to understand that distinction about simulator. You can also learn from other people's experience, which basically means it's not a simulator, but some people have lived and they left their traces. You act as if they are your traces and try to learn the policy from it or the model from it. In fact, in AlphaGo, originally, they would take other expert players plays and use that as the seed. AlphaGo is a case where actually the simulator itself is cyber. There is no real world. The world is already, cerebral. So AlphaGo actually can learn from quote unquote experience. When it does self-play, that's exactly what it is. But it does both. If you using self-play, it's just learning from its experience. If it is using traces of somebody else, it's learning from somebody else. Okay. And then the extreme case of learning from other people's experience could be that basically in the case of AlphaGo, at least people who are playing the game for which you're trying to compute the policy. What if you just hung around looking at what everybody in the world is doing every waking minute? Sometimes they'll be playing AlphaGo, sometimes they'll be eating, sometimes they'll be going to Starbucks, sometimes they'll be diffusing bombs in the toilet. You do all of this, you learn all of this, basically use all of this and try to learn from this huge, massive model of the dynamics of the common sense world in general. Looks like a very darn hard thing to do. Nobody thought that sort of thing will go anywhere. But interestingly, we do have these large scale language models, LLMs, large language models, are more interestingly LSSM, which is actually the terminology that I really like, which is large self-supervised models, because it doesn't have to be just about language. It can be any sequential state trajectory. By the way, state trajectory is like a sentence. State, action, that's like a planning sentence. And not surprisingly, if you see a huge number of those kinds of plans, you can, after seeing the last action, you can predict the next action. Just as you predict the next goal. We have done this, like people have done this long back. Even in our group, we have done this before, way before the advent of LLMs. For example, you do this as word vectors, where a whole bunch of these plans are kicking around. The tricky part is if you're just doing this for one problem, the question of is it easier to just give a simulator or a model, or is it easier to give million plan traces? That's very hard to say. It's actually easier to give million plan traces. Do you understand what I just said? No, what I'm saying is that for a specific problem, it's probably easier for me to just tell you the rules of the game than to give you a million, sequences. On the other hand, for the entire common sense world that we take for granted, which by the way is only like a base case, people don't get paid for doing common sense stuff, right? They lose jobs for not having common sense, but they don't get jobs for having common sense. They get jobs for random coding questions. It's not common sense like at all. You understand what I'm saying? So the economics of which is easier, writing the model or learning the model directly, or learning it from huge number of traces that somebody else happens to give you. If somebody has to give you those traces, it's not easy for them, very possible. If on the other hand, one of the greatest things, or the saddest things, is that, you put every damn waking movement of our life on the web. I like to think of the World Wide Web essentially as our collective Jungian subconscious. Everything that we think of, the good, the bad, the ugly, is up there. As sequences, of state action, state action, state action. So you can learn potentially completion model using LLM kinds of stuff. You can, and they may not, there's no guarantees whatsoever that they will work for your specific domain. But they may work for the kinds of things people do without actually going to school. Such as, can you get me a glass of water? You don't need to go to trade school to figure out the plans of getting you enough. But it's a useful thing that you might want to ask your household. So the most extreme case of learning from other people's experience is this learning LLMs. LLMs essentially are learning these, very opaque models. They're not yet the world models yet. They only predict the next action. And there are no validity guarantees. In fact, in a minute I'll tell you that LLMs do extremely badly if you describe the problem to them. Just like AlphaGo would do extremely badly, Deep Blue will do extremely badly if you say, yeah, it's the same rules, but I want to spell happy with my pieces and the other guys. Flexibility. You understand? Okay. That's from other people's experience. That's the extreme cases of LLMs. And by the way, I should mention, this is a parenthetical comment, that when you're learning the world models, that's in reinforcement learning terminology, that's like learning the transaction model. In reinforcement learning, the classic reinforcement learning, you don't learn the rewards, you experience it. If you don't believe me when I said reinforcement learning, the true reinforcement learning required experiencing the world, how would you experience what it feels like to eat ice cream by me looking at you eating ice cream? There's like a lovely passage in Good Will Hunting. There's this lovely passage where Robin Williams basically talks to Matt Damon character about, you have theory, but you don't have experience. You read in the books about ice cream. You don't know what ice cream tastes like. And the books say that you are supposed to feel good about ice cream. You might say, well, maybe like 15 points reward for it. But really, some people just have much higher reward for it. For ice cream, some people don't have any. People with bad teeth, very low reward with ice cream. Okay, my point is that rewards in standard reinforcement learning are not really learned in any non-trivial way. They just experience. The moment you go to the state, the reward washes away. Just washes away. You don't say, I keep eating ice cream until to figure out what actually is good about ice cream. If on the other hand, you're trying to learn from other people's experience, you don't know why they're doing what they do. They have a reward method. You try to not only learn the dynamics of the world, they try to learn what it is that people seem to like. What is their reward method? What makes them happy? That is a learning too. But it's actually called plan recognition. That means you're trying to plan or goal recognition. You see what people are doing and try to figure out what goal they're trying to do. And other terminology for the same thing is inverse reinforcement learning. Right? It's just learning. There are two things you have to learn. One is called reinforcement learning. The other one, if you're learning, that's called inverse reinforcement learning. Why? It's as bad as in the intro to AI, I tell you. Uniform class search assumes non-uniform class edges. Crazy nonsense. Once you give the name, people get it. So everybody keeps saying, I am just learning the goals. I am is learning what makes you happy. You don't need to learn what makes you happy. You can experience it. But if you're trying to learn what makes your boss happy, learn. It's not what I'm saying. This is good stuff, my friends. It's very general sort of right now. So it's kind of probably frustrating for some of you. Where is the algorithm? Where is the neural network? What is the number of layers? What type of parameters? But this stuff transcends a whole bunch of these dimensions, and hopefully you'll make sense of it. If any of you are getting like close to about 80% of what I'm saying, you should write papers. Seriously. Right? And if you're getting, around 40–30%, you're okay. Because you should just come back and understand. These are things that people don't realize. There are a few people who realize, but not everyone. Yes.
Might be a stretch, but is like learning from other people kind of like looking at correlation instead of causality.
No, that's a very different issue. Correlation and causality are a completely orthogonal issue. In general, actually, it's actually an interesting point is, I will answer that in the following way. In planning, we don't talk much about causality. Why? You did the action. Before the action, this was the state. You did the action, this new state happened. The action caused the damn state. Unless there are other agents. I actually consider the word, the phrase causal reinforcement learning an oxymoron. Reinforcement learning has to be causal. If it is true reinforcement learning. If on the other hand, you're learning from other people's experience, it's actually very hard to tell what is causal and what is not causal. Then it becomes hard. But it's important for you to understand that standard order, most of standard order is supposed to work if you are experiencing the world. If you don't understand that, you're asking yourself, why? I mean, if I'm anyway feeling the reward, why am I learning the reward? Feeling the reward is not learning. Right? Learning is done only if you don't get to experience the reward. Trying to make sense of other people's. By the way, this is another thing that I say in the class, in the intro to AI, and I'll tell you for the rest of you who are not there in intro to AI, that when people come to me, they have their capability, the kinds of actions they can do. They have their rewards, what makes them happy. I rarely care about their capability. The most interesting thing about you, in general, but as a human being, most of our capabilities are more or less the same. I understand that we think of, oh, Michael Jordan is not better at basketball. How often do you care about basketball in life? Most of what makes you you is not your capability, it's your rewards. The rewards that you see. If I need to understand, if I need to work with you, the thing that matters is figuring out your reward. So I have to do inverse reinforcement learning on you. That's how we get along and be good to each other. You see what I'm saying? Because I'm trying to understand what is your reward metric that makes you do what you do. Because what I really want to know is what your reward metric. And the only way I can learn is to see what you do. That's the indirect evidence of what you must be, what must be giving you happiness. Okay, so it's your reward metric that matters to me more than your capabilities, because most of our capabilities are more or less the same. There are minor changes, but that's not less interesting. The variation is much higher in the reward metrics. But planning continue. Problem classes. The planning problems differ into different fields. People build their own different fields because they're doing planning, but a very particular class of problem. An example is motion planning. So in all these cases, the special class of the special class would be subsumed by all we have said till now. You can still talk about world model, you can still talk about goals, all that stuff. Everything that we talk about. Except there are additional, it's sort of, instead of being just directly domain specific, it is domain class specific. You understand what I'm saying? So motion planning people basically look at motion planning examples, motion planning scenarios. What is the motion planning domain class? In some high dimension, in the simplest case, is there's a two-dimensional space and you're trying to go from one to one. The general motion planning is if you basically have a robot with multiple joints, then essentially, even if the robot is a three-dimensional space, it is effectively operating in a high-dimensional space. Because every joint is essentially a different, freedom. So then you are essentially trying to figure out what is the fine path from one particular configuration of the robot to another particular configuration of the robot in this high dimensional space. Remember when you did a star search, the first example that you did was a simple grid. It's start point here, goal point here, and you can go, up, down, left, right. That's motion planning. Except motion planning people never grew up from there. They just stuck there. They only want to do that. They want to do it for big, big maps. They want to do high dimensional maps. They want to do it for probably multiple agents trying to do optimal plans at the same time. For example, you guys know that Amazon warehouse robots. There are tons and tons of warehouse robots going all over the place, and there's like a centralized thing which is trying to make these plans. Either centralized or partially, agent specific one. It's trying to make this map F, that multi-agent fact-finding problem. Effective, fast way in which everybody can go to their goals without bumping into them. So that's basically one class of problems called motion planning. And there's a generally robotics people typically tend to be a lot more interested in this because much of the front and center thing about robotics is first it needs to move. Okay, but it's not a problem. It actually falls in the same state of concerns. It's just that there are special additional structures that we can explore. For example, one of the ideas that we might get to look at is like this idea called rapid random trees, RRT algorithm. It works very well for motion planning. And one of the interesting things is once you realize motion planning is just in the same big planning space in just one branch, then you can ask what would be the RRT equivalent for some other problem. Things like Monte Carlo search are kind of connected. Monte Carlo search is kind of. Okay, so you can actually do the sort of a transfer of ideas from class. So in robotics, there's the motion planning, find a path in high dimension. You also have task planning, which is find a sequence of actions, of general actions, in addition to just moving. So for example, pick some, cup from somewhere and put it somewhere else. So robotics people typically tend to say, we'll work on motion planning, one of these days we'll combine task planning. And there are a bunch of other people that you call operator-based planning, people who just work on operator task planning, and one of these days we combine it with. Neither of them ever actually bothered to combine. So in fact, combining motion and task planning is still a big research. Because the overall plan, the robot just that only moves and does nothing is useless. The robot wants to do stuff but can't move, is also useless. You see what I'm saying? But I mean, these, if you look at the literatures, these will look very different literature. They're published in different places, etc. But the general constraint, the general structure of the problems are very same. There's this additional structure for this. They said combining both types remains a funny. And then the planning versus scheduling. It's something that I mentioned earlier. This is another dimension that you want to understand, which is planning is finding a course of action. In general, you should assume that if it's a valid plan, you also make sure that the resources are available. Scheduling is assuming that you have a plan, trying to check whether the resources are available to execute the plan, and assigning, who does what. For example, suppose I have a plan for, let's say there's a bunch of stuff on the boards, and I have a plan that I came up with a plan for, writing the boards. And that requires like 8 students, 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, and they're all writing them. That's my plan. Except I need 8 students who have nothing else to do, then listen to me and then start writing. Then I say, I'm about to start the plan and all of you leave, I have no resources. If I do have some of you sitting here, then I'll say, well, you 4 go there, you 4 go there. That's scheduling. You see what I'm saying? There are lots and lots. So, for example, what courses to teach is a planning problem. Which room to teach it in? Who teaches it? It's a scheduling problem. Timetabling is a scheduling problem. You see what I'm saying? Of course, there are connections between the planning and scheduling because not everybody can teach every course. Right? But in general, these fields evolved somewhat separately. The planning people tend to assume somebody else will be able to do the scheduling. We just break the plan. But if it's not schedulable, then it's an infeasible plan. Scheduling people think that we just wait until they figure out what courses have been done by whom, and then we just find the rooms, for example. But the overall problem is combining. But there are good enough applications just for scheduling that scheduling is a whole damn area by itself. There's tons and tons of places where somebody else decides what needs to be done. All that matters is allocation of resources. That's just scheduling. Interestingly, for certain class of problems, scheduling is NP hard. Even some of the simplest classes of problems, scheduling is NP hard. Planning is easiest, which is as it should be. Planning is bigger than scheduling. Yes.
Sir, when we are planning things, we generally have constraint and the states that sort of show what are the resources that are out there.
Yes, but the point is typically one of the things all of us do is so for example, I go to San Francisco. What's my travel plan? Which flight I'm taking. Have I figured out exactly when I come out of the home, which time do I ask for the Uber? How do I get into the car? Where do I get off in the airport? Those are important. If in fact I made a very nice plan, Uber is on strike, I won't be executable. So honestly, the right guy planning would be that I will actually, this is the full detailed plan. I am going to take Delta 2880 and the Uber car number 75 with the driver D7, where I sit in this particular position in the taxi, and then I get off at the door number 7. You can go into the level of detail you want. Most of the time, you ignore these details and just plan at the high level. When you do that, you are assuming that the low-level details will more or less be fillable without having to change the plan. That's mostly true, but not always. You see what I'm saying? So, in fact, I'll be missing one of the classes. I'll be missing lots and lots of classes, but while missing one of the classes. Okay. When I'll be in India, and I'm supposed to be in Calcutta, and I made the plan. I already picked my flight and everything, and I'm going to go from Calcutta to Kharagpur. And then my mother-in-law tells me that that particular day there is a festival, and people who run taxis won't come to the airport from Kharagpur all the way to Calcutta until 3:30 in the afternoon. How the heck could I have thought about this? You see what I'm saying? If I tell her, tell me all your constraints, she'll say, tell me what your plan is. That's why we separate time and schedule. And now we are going to have this back and forth, trying to figure out some variation of my plan that doesn't change the flight, but somehow still hang around in the airport for a longer time until we say something. That's real work. My plan actually failed, right? I'm just saying, yeah, it's okay. I'll hang around doing nothing and then I will retire. So that's why we separate, because the life becomes easier if you can decouple planning and scheduling. That's why we separate motion planning and task planning, because life becomes easier if you separate motion planning and task planning. But the world is completely connected. So in the very possible worst case, everything is connected to everything else, the butterfly effect. But if the world is truly, fully connected, you won't be here. You understand what I'm saying? Because evolutionarily, there is no way that any of our ancestors would have survived if everything is connected to everything else. If it's only because it's loosely connected. Some of our ancestors, actually all our ancestors were alive. And there are people who are not in this classroom whose ancestors are not alive, right? And they basically, at least before childbearing age, color, got eaten by a tiger, passing tiger. Okay. Good. And that's good note, planning and scheduling, planning in general, substitute scheduling, although high level plans may leave out scheduling details for later phase. And the question is, when is it right? It's right, statistically speaking, most of the time you will be able to provide it. And in sort of, when you're trying to separate a combined problem into a loosely coupled pieces, optimality becomes a hard thing. Because it may well be the case that you took everything into consideration, you could have come up with a more optimal final plan. But it would also be much harder. In my case, had I essentially kind of tried to take, if I was omniscient, and I was able to figure out all the constraints of correct course access, summing to etc., I would have come up with a plan that would be the best without me having to hang around. I mean, nobody really likes to hang around here for nothing. So I do have a side constraint, a preference of not hanging around. So I could have got a more optimal plan. But it was a much better assumption to assume that once I get there, I can. That's why you separate planning and scheduling. Planning horizons, long-term planning versus immediate horizon planning. Basically, you guys have big plans, and you also have little plans, and you also have micro plans. You also have very small things. Like you're like, what's your plan? Well, I mean, for MS actually it's very simple. As I told you, the MS plan already, right? I mean, you have to do the coding interview, you have to get the job, you get the internship, and you get the thing, and that's your plan. And in between, you'll say, I'm interested in some course or other. That's fine, but that's a big plan. Okay, but then that doesn't still tell you what to do this evening. But are you going to go to, are you going to make this kind of food? Are you going to go to this kind of restaurant? When are you going to leave the class? All this stuff that you work out. That's so the horizon of the planning matters. And again, it's the same issue. In fact, optimal plan for your entire life would require everything right. Your hope is that where you eat today is probably not going to affect whether you get your internship converted into a full job. But man, if I'm really mad at you, I'll make that big money. You see what I'm saying? So it's pathological cases anyway. Okay. So horizons matter, long-term planning versus immediate horizon planning. And as I said, sometimes you have both of them. You're making plans at different levels of coarseness of the time. Okay. And then actually one of the interesting things about that is that actions themselves have duration. We didn't talk about this, but we kind of, we'll talk about it in a minute. But when you start an action of doing MS, it's not an instantaneous action. Let's not even talk about doing PhD, which is even not at all instantaneous action. Like, no, don't combine stochastic with instantaneous. Those are very different things. It's not apples, it's apples for oranges. Instantaneous action means you do this, it's done. Durative action means the action itself takes a long time. You can have durative deterministic actions. You can have instantaneous stochastic actions. One of the things is to be able to talk such that we make sense, right? I mean, so these are. I'm hoping that you get that. Right? Essentially, these are different, dimensions. Okay, that's that, right? Okay. Actually, I should mention that the closest anybody comes to planning is the robots running on these infinitely tessellated floors, that you get to see from several of the robotics reinforcement learning-based robotics people. Is how to kind of fall your way from here to there. That's it. When is this robot going to make a plan about getting an internship and getting a job? That's really long term. You understand what I'm saying? The difference is, yes, they're all plans, but the duration time duration that we're talking about matters quite a bit. And of course, when you have larger time durations, there's much more uncertainty about how the world evolves too. Okay. This is the last what is planning. You probably wonder why the heck did I ask what is planning? But okay. Environment types. The one stuff that you actually knew, I put it at the end. Which is planning problems change based on the environment types. That's what you've been talking about. Deterministic versus stochastic. If it's a deterministic world, you can just get by with a line plan. Assuming full observability. Okay. If it's a stochastic world, you need a policy. Because after doing the action, you don't know which state you will be in. You understand what I'm saying? If it's a fully observable deterministic, then certainly it's a line plan. Okay. Fully observable versus partially observable is the difference between whether you're searching in the space of world states or searching in the space of belief states. Is a belief state. Belief state is a set of states that you think you might be, one of which you might be. In the most general case, a belief state is a distribution, a probabilistic distribution over the set of. You change the distribution, they change the. You see what I'm saying? So if you don't have eyes, you're basically converting your problem from searching the space of states into searching the space of beliefs. Okay. Static versus dynamic. That basically, if you're not doing anything, is the world moving. If it's moving, it's dynamic. If it's not, it's static. Obviously, static is much better. Okay. And then if you have dynamic, it could be of two possible reasons. Of course, you know the other agent. I mean, so it could be that because there's no other agents, it's just the world has a process that controls the way it moves. Or you know the other agent and you can model the other agent. Sometimes there are too many agents, you don't feel like modeling them, you act as if it's a process. Traffic. Traffic is caused by thinking people like you and me, barely thinking people like you and me. Rather than actually model every one of us, you just think of it as essentially some sort of a stochastic process. There, the world is moving, but it's not, you're not modeling the agent. There are a few agents and you know how to model them, then you start thinking of multi-agent planning. If one of the agents is a human, that is actually very close to my heart. We will talk a lot about it in this course, which is human in the loop planning. So maybe your computer is trying to help you come up with a plan. And it gives you some answers. That's what actually I already told you. The Pareto frontier case. We're trying to come up with a travel plan to present to the user. Right? So if basically to do well there, you need to learn the user's preferences beforehand. Like as I say, in those days when there used to be a travel agent, human travel agent, the first time when they ask you what kind of break you want to take, etc., I can deal with it. After I deal with them for like 10, 15 times, they still act as if I'm a stranger, I'll get it. Because they haven't modeled me at all. Might say modeling is profiling, they are kind of profiling me well. Profiling is how life becomes easier for you. But I can also make your life be, I use persuasion technology, you can use the profiling to do things that you probably don't. Profiling is important to actually be supported. Okay. In general, actually, we'll talk about the fact that collaborative planning with humans in the loop essentially will involve the computer having a mental model of what the humans are trying to do in addition to what it is right. And trying to combine both of them in coming up with a plan. You see what I'm saying? There are all sorts of interesting things. So what is optimal for the computer? The robot might not be the right one because the human in the loop gets spooked by that particular plan. For example, my favorite example is if I have some flick of dust on my nose, and Baxter, the robot, comes hulking with his big hand and tries to remove the dust, most of that from my nose. It's really a very nice, helpful thing, and I just scream and start laughing. But if it does it for 8, 9 times and I didn't die in any of them, the 10th time it doesn't do, I get mad at it. What's wrong with you? Then why aren't you doing it? I still have us. So I am modeling the robot is modeling me, and that's how collaborative planning is. And one of the other interesting questions is that if there are, when you provide options to humans, you might ask, why not this other kind of plan? Right? They'll say, here are the 3 different plans, and you say, no, is there a plan that takes me on United and has a lower time in Chicago? That's what is called a counterfactual or a contrastive query. So the robot has 2 possibilities there. The AI system has 2 possibilities. One is it can try to prove to you that such a plan would be worse than the plans that are presented to you. It would be not on the peripheral. First one. And the second is, even though it isn't, I kind of realize that you seem to have a thing for United. So maybe I should take your request as an indirect specification of your preference. Every time customer speaks to you, they're giving you useful. Your AI system with a human in the loop, human in your head. You can learn from that and actually do better decision support. So when you have this, typically there's an entire area called decision support systems. They're not doing the planning themselves, they're making the plans that you would execute, you, the human, will execute. Where you may have some ideas yourself, it's trying to help you come up with a plan. In fact, many things that we do in real life are actually planning aids. Like route planning is a planning aid. You don't necessarily just take what Google asks you to do. Right? And it turns out there are interesting constraints separately about that. You could, for example, in some cases, explainability is important. You need to understand, why did this plan make sense? Why did you come up with this kind of thing? In fact, one of the most inexplicable things about route planning that I have felt, and I'm sure you did too, is they don't have longitudinal memory. So if the expected time for me to come from my home to the university in my normal path is 1 microsecond longer than a completely different path that I never take. The system says that's no good. I actually like my path. In fact, it becomes easier for me to do system 1 driving if I'm in a known path. If I'm put on a new path, I'm likely to get more accidents. The system should know enough about me that in the last few times, God knows how long the dog has been taking this path. I agree that it's a few minutes longer, but maybe it's better to do this, unless this path is fully full. But you know that our planners actually change. Like the other day, I and my wife were both going to go to the same particular place. We both came out at the same time. Her planner said, go that direction, my planner said, go this direction. And I was just trying to kind of follow her so that he'll at least be the same path. It's not that the system will either me or my wife. Each of the systems have slightly different models of the traffic, and they were just. Okay. So that matters. Those kinds of things matter if you have humans in the loop. Okay. One of the other connections. By the way, everything that I'm saying, we will get to talk about some specific paper or some specific technique that will fall into these pieces. But then you look at them as a bunch of papers, they all look like different parts. But if you look at this organization, they can be a okay. So one more interesting thing, if in fact humans are working with decision support system. And by the way, classification systems are different. We use classification systems whether to give loan or not give loan. Think whether this person is good or bad. They will support you. And whether to take the classified advice is up to you. And remember, for the classification systems, you have to think of classification systems as one action plan. It's one action plan. Planning is multi-action plan, that's a policy. Classification systems can be unethical, if they can be biased, if they can be unsafe. Classification system decision should make sense to you, and it's not because you don't know how the heck is working. But learning. You understand what I'm saying? So in fact, one of the papers that we'll present here that that's work from our group is you have a planner which actually uses some deep reinforcement learning technique. So its internal representations don't make any sense to the humans. It's playing some Atari game, it learned some model and policy, and then showing you that. The human doesn't like the action that is suggesting. The human says, why are you suggesting that? First of all, humans will pass in this symbolic terms. Why aren't you doing this action when it's the following, this agent? The system is not actually thinking in those terms, if at all is. If you can anthropomorphize it, it's not at all. So the question then becomes, whose responsibility is it to make sense to the other? If you and I don't understand what each other are asking, it's mutual responsibility to make sense of it. But as an AI system is there, I think it's hard enough that I have to deal with all of you and try to figure out, why don't we make sense to each other? If each stupid AI system, I also have to do the same kind of thing, what sort of technology is what's in my life? I want the system to do the heavy lifting. Even in the human interaction, sometimes basically one person actually does more of the heavy lifting to make sense that you understand what they are saying. You just sit there, teaching the class case in point, sitting there and I'm doing the heavy lifting. The wrong kind probably, but some heavy lifting. Right? So the interesting question then is, if an AI system is trying to come up with a plan and the human doesn't like it and the human wants to give advice, the advice would be in a higher level symbolic. Not in some pixel differences. And if the reason why this thing made a decision is because of some pixel differences, that doesn't make sense to the human. The salient, the attention doesn't make sense. They might be thinking. So one interesting case is, even if in fact for the accuracy reasons, the system uses its own representations, because it's living with us, it should basically take advice in terms that we want to give it and give explanations in terms of others. The alternative would be that every time anything happens, you stop doing whatever you are doing, try to change some parameter of the 15th layer of the network and see what happens. I try to kind of look at, an activation map of 15th layer of the network to see why. I know I can do that. I'm not allowed to do this for you guys. I can't do lobotomy. I can do lobotomy on the neural networks. You oftentimes think that the fact that you can't do lobotomy on people is like kind of bad. It's actually great. No, lobotomy now falls on your hands and it's very, very painful, for your life. It's good that I don't need to deal with what's going on in your head. You will talk to me in terms of I'm not in terms of. And it's the same thing for machines. In fact, in the machine skills, here I'm not even allowed to do it. So it's good that the constraint says it's not my responsibility to figure out exactly what is happening in this thing, unless you are stupid enough to buy one of the devices that Elon Musk apparently is going to make, and then there will be like a little screen on your head saying what you're thinking. Right? It's good that I don't need to know what you're thinking. I just need to, it's good as well as bad. But we mostly think people tend to think the bad part. Oh, I don't know exactly what you're doing. It's actually good that you have a life. Otherwise, you have to think of what everybody is doing. Actually open your life. Because you can. In the AI system state, you can. You should. That you have a life of your own. They should do the heavy work. To the extent human reasoning typically tends to human explanation typically tend to be symbolic. If whether or not the system is doing symbolic reasoning, it should be able to accept advice in symbolic. It should be able to give explanation to it. That's a really useful. And we know that winds up opening interesting research developments. Okay. And then finally, since I kind of talked about that, the input resolution language, I understand that these things are taking models, etc., etc. The question, of course, is what language is the model in? You already kind of heard me say that, during this whole long discussion, it means some kind of a symbolic model. Or they can be essentially some large, big learned neural network. And there's anywhere in between, part symbolic, part neural network. So the resolution of the learned model can be just from the purely sensory input, pixel signals, etc. Can be symbolic input. That means actually when humans are giving the models, they're much easier for them to see the model in symbolic language. Or it could be a mix. Depending on this, the planning algorithm. Okay. Any questions? Okay. So a few more slides. For the day, which is operator-based learning. Otherwise, we'll stop. But I still have a few slides. One of it is, why should we care about planning? Given all the stuff you now know about planning. Before you came into the class, you may have an idea, but now I gave you a little more nuanced idea for the different kinds of dimensions. Why should we care about planning? Why can't we just wait for some DALI GPT-3 clone just do planning for us? That's a reasonable thing, right? If you wait, then you don't have to think, and your brain will be kind of unused, and it will be nice and fresh. So the answer actually is that planning still remains a hurdle. It becomes it's one of these big hurdles. Everybody talks about the fact that learning world models is important. And learning world models from the kind of data LLMs use is not possible, is not useful. It is not possible because they have basically linguistic data. World models are about transition, not transition between word to word to word. That's just a description. I need the internal transition of this data the word going. Yes, there are sequences. I mean, you have state action thing, that will be a sequence. But those are not the sequences that people put on the web. The stuff they put is huge amounts of text, words that make sense, sequences of words that make sense to me. And they're just learning, and then these systems try to tell you what happens. Now, if you have played with LLMs, etc., you, for example, know that they can be prompted. There is a whole entire prompt engineering now, right? You can ask them nicely. They can do things that you didn't think they were actually designed for. So the question is, what if you ask them nicely? Would they do planning too? I gave you a reason as to why they can't. Because they're not in a transition model. The other is that, in fact, is Karthik here? So one of the people, there, Karthik, for example. So he and basically essentially just looked at GPT-3, gave it very toy domains such as block stacking plans. You describe the scenario and ask what is the plan. They are like ridiculously bad. It's not surprising. So it's a reasonable thing. If I learn this whole technology, if LLMs are going to do it anyway, what should I do? It's one of the, I think, how many of you seen Humans series on Amazon? should see that. It's one of the first season of humans is very nice. They're basically talked about this world where synths that like robots are almost as good as us, but are not allowed. It's almost sort of a West world stuff, but it's like different. But the one interesting point in the beginning of the series is this girl, the parents ask her, why don't you go for, you have a grade, why don't you go for the med school? And says, why should I go for med school? I spent 5 years going through the medical degree, another 4 years figuring out the surgery, during which time robots become even better at surgery than they already are, and I won't be able to do surgery. Reasonable point, right? I mean, it's like, why should you do this, right? And so I'm actually giving you, before this course is over, if LLMs are able to do planning, then you will be like, taking a simpler course. I think I can reason. It's very hard given what demand AI is really kind of actual guarantees, but I would say for the semester, I will make sure that relevant won't be like, so your service. And there are good reasons. In fact, there's actually an article that describes Karthik's work that you can look up. Okay. Okay. Any questions? How many people? Okay, go ahead.
When you say large self-supervised model, I kind of feel it is more related to the world models than it is to the LLM.
No, it's just sequence. The question is what sequence is it being trained on? If the sequence is a sequence of words, then you just predict the next word.
So
If the sequence is a sequence of actions, yes, it will predict the next action. The question is who gave you the sequence? Who put on the bell tons and tons and tons of land?
So it is still something that is supposed to be done, or the LLM are the large self-supervised model.
So basically, again, the terminology is LLMs. This came up in the language. Language is sequential, except in arrival. How many of this in arrival? That's not sequential language. Okay, but everywhere else, language is sequential. The major base difference is sequential this way or sequential this way. A sequential this way. That's the different languages. But so they applied it for the linguistic data because it's available. But it's saying that I can predict the next word is very different from saying I know how the word works. Language describes the word. Going from the description of the language to the actual word model is quite a hard. The simplest thing would be if people put tons and tons and tons of behavior traces on the language. But the dirty secret modern AI is we can only use what is available that people didn't know that you would be using. They'll now complain, why the heck are you using my stuff? Have you guys seen this whole thing where one, I think Simon Stalenberg, who is a science fiction artist, he's developed all sorts of very interesting futuristic, images, etc. Of how the world might look like using his imagination. And then, everybody is supposed to be impressed with Gary. Everybody is supposed to be impressed with stable diffusion. He's supposed to be impressed with fusion. He said, yeah, you guys be impressed. I feel like it's stealing my stuff because you just trained the damn system on my pictures. You understand? I never gave you the, permission to do it. The interesting thing, the ethical thing that we are actually kind of skipping is all the data that was put on the web is just apparently free for everybody. And the people can make money off of it. We never said it in right. We never did say that you can't use it, but it was just there and people can use it. And there are all sorts of interesting questions of that kind, basically. Even in this case, we actually just put the paintings that he painted and they were just training off of. Not just him, but other people. But he is the one who complained, and people were very surprised saying, you're a Luddite. You're against technology. Yeah, everybody is for technology, it's not their job. That's going away fast. You understand what I'm saying? Tell me when your job is going away, even though I'm going down. transition periods are very hard. And we haven't talked about, the ethical aspect of this. And one of the very interesting things is there is a push to make data use more and more restricted because we now realize that's not free. It shouldn't be free. When radios were invented, spectrum was free. Anybody can use the spectrum. Then we realized people were using this spectrum and making money. They're making money, and the spectrum belongs to all of us, so we do spectrum auction. This could happen. So then you will have to get a bunch of factors who have nothing else to do. Say, do something else so that they can be fun. You will not forget. And then I might say, look, we can just write for you a simulator. That will be easier for us. Which is the other possibility. If it is a single task, it's easier to just tell you how to do the task than to give you, because you don't know anything else, give you a million traces of that model. If this is hurting your head, it's supposed to. Because it's anybody can be impressed after tweets about, oh, this is where are we like? You won't know where we're going unless you know where we're coming. What are the issues? Okay. Anyway, what will you learn all of this basically? Okay. So in particular, some of the technical topics we'll talk about. The very first thing I'll do is operator-based planning, where we'll think of actions. The world model is represented as an action with preconditions and effects. Goals are represented as what needs to be in the final state. Then it becomes a simple search problem. We'll start from there. Okay. And then actually you can do all sorts of interesting things like replanning and all that stuff within that context. And in fact, I'll also do within that same planning, I can talk about decision support. We'll actually talk about human in the loop for operator-based, for example. Right? We can look at motion planning. Once we can talk about stochastic scenarios, stochastic planning scenarios, for which I will do a quick review of Markov decision processes and RL stuff. But again, you have to realize that anytime you are learning the model, you're kind of doing some sort of reinforcement. There's like a spectrum. It's not like if it's not in Sutton's book, it's not reinforcement. Okay. Then, as I said, we're talking about learning models. You can learn operators, you can learn goals. If you're learning goals, then it's plan recognition. If you're learning operators from the traces, that is basically learning operators from traces. It actually works for that. You can learn transition function. Learning transition function is actually learning operators, except operators are at a higher level. If you learn the transition function, you call it reinforcement. If you learn operators, you call it operator. The same. Syntax is, the words are different, but they're essentially doing the same. And if you're learning reward, that's like learning the goal. Plan recognition learns the goal. Plan and goal recognition learns the goals. Learning reward is inverse reinforcement. As I said, that's a very bad name, but that's what we'll talk about that too. Then we'll talk, in some sense, it would be very interesting to compare your brain before this class and after this class. In addition to being fried and bored to death, does it have a lot more interesting connections between what you thought was reinforcement and what you thought was planning? That's what I did most of the class. There really isn't. I mean, you already know a lot more than people who come to reinforcement learning just from reinforcement by reading just Sutton. By the way, interestingly, Richard Sutton knows all this. When he used to come for planning for tasks and planning functions, I mean, it was like he was basically, from his perspective, all of these are just as well. It's the newbies who essentially need one paper. Yeah, this stuff looks good. So you could do whatever you want. If you're doing operator learning, you just I'm doing RF, and nobody knows the difference. In the industry, nobody knows what. We just avoid going to maybe do that or something, Okay. So anyway, those are all connections there. Planning with humans in the loop is something that I'm going to spend a bunch of time on because we actually do work on that, and I want you to understand that. It's very important. Just as classifier systems aren't working in the world directly, they're just telling you what to do with the classification. And there are all sorts of interesting issues about ethics and stuff. They come in planning too, because sequential decision making is more general than just a single shot classification. Okay. And then I said explanations and advice taking when planner and the human have different representations. I talked about it, and we'll talk about how to do that. We'll talk about some papers. And last minute I said planning in the age of LLMs. We'll do a little of that. At least we'll tell what article done. Things might change over the time during the semester. This is a moving target. It's like a part of the Confucian thing of maybe living in interesting times. We are living in this. Okay, but there's a difference between just thinking whatever came on Twitter today is the field versus knowing that is the tip of a big intellectual iceberg. Course is supposed to be that. That's why this is not going to be useful once again for your coding business. And if you're doing this for that, do something else. Unnecessarily taxes your brain. It's not worth it. Okay. And then I might do something about open worlds too. That's basically the kinds of tax things that I'm going to do. Okay. In fact, I should mention that when I'm looking at operator-based planning, as I said, we can talk about different domain dynamics. I will, in addition to doing deterministic, I'll also do stochastic, I'll also do temporal planning. Because as somebody said, none of you have thought about doing plans when there are actions with duration. You live with actions with duration. Cooking involves actions with duration. You start boiling the water and you start cutting the potatoes. You don't wait for the water to be boiled before you cut the water. Certain things can be done in parallel. And in particular, they can be done while one action is going on, multiple actions can do this time. You haven't thought about it, so I'll make you think about it. So it turns out that what goes for MVP is really atomic level understanding. That means black box states with actions going to black box. Operator-based planning is what's called a factored representation, where you essentially have a representation for states, and then the action is taken from that representation. Until neural networks came along, basically representation means you decided what the representation is, and that's something that makes sense to do. Now, when you say representation, it is learning the representation. Problem with learning representation is what you learn doesn't have to make sense to me at all. You understand what I'm saying? All AI systems have learned some representation. They're doing some reasoning with that. If the human is in the loop, they want to have some guarantees that it's making sense, etc. You need to learn the connection between their representations and your representation. And as I said earlier, that heavyweight lifting should be done by the machine, not you. Because every system learns a different representation. Why the heck are you wasting time trying to figure out how the way you think about the world corresponds to how this program works, this program works. Okay. So we'll do that. So that's basically what you learn. And if it's not, as should be obvious to you, but what I did today, that all this is done in the context of big boundaries and a syncretic view. I hate either people who say, neural network is a passing page, passing pad, let's not think about it. Or people who say, that's it, nothing else needs to be learned. You need to know both. You need to know the whole thing. That's what learning is all about, right? So we will do it that way. So we will, for example, talk about symbol versus neural representations, model versus model free, plans versus, why even plan? Why can't you just reflectively react, like model? Some of these things will be in the background as we go through. There are multiple sister areas for this course, automated planning, constraint satisfaction, etc. are connected, learning, reinforcement learning, even supervised learning is connected because, you could actually be looking at traces and converting that into value, the function that would be supervised learning. Control theory is actually well connected, although I won't talk too much directly about it. So one aspect that I didn't talk as much about is discrete versus continuous. That's an actual distinction that is important. Much of the stuff like operator-based planning, etc., assumes discrete dynamics. If you have continuous dynamics, things change. Sometimes continuous timings are more important. For example, locomotion, if you're very well, that you know, continuous timings. As you're falling, you don't fall in like steps. Okay. Control theory actually takes much more interest in the continuous dynamics. Human factors is very relevant if the human is in the loop. Teaching format. It should be obvious by now what the teaching format looks like. The graduate class, we're expected to have done intro to AI with the approximate coverage of what I teach in CSE574. While I will briefly review some of the relevant topics sometimes, or at least tell you which lectures to you, this thing, I am not trying to make you learn intro to AI as well as the stuff that I'm not. This will work best as a second course for people, where they thought, why are we doing these things earlier on? And then they may become connected. So that's the best way to do it. I will teach most of the several of the introductory classes, actually many of the classes, but I will also have presentations. And now, as the presentations come, the simplest thing I could do is ask each of you to present a paper. You feel good? I don't have to do anything. Nobody learns nothing. Because if you do, then you don't have to take this course. I never understood what this idea of people who don't know the area reading a paper and presenting to others. Actually, understanding is hard enough. Understanding at a level, if you can present it to other people, is even harder. So every time you think, oh, I presented other people's paper to my classroom, my classmates in other courses, kind of hit yourself back. You probably just wasted your time. And mostly what people do is they say, okay, I will give you a good grade for your presentation, you give me a good grade for it. This is like the 5 for 5 on the Uber. Right? That's exactly what happened. I could do that. In fact, you have enough people that, man, I can have 3-4 semesters worth of presentation. Yes. I would probably not do that unless I know very well the competence of it. Okay? More likely what I'm going to do is I will have my seniors present some papers that they work, with the background. That will likely happen. But when that happens, you will read the paper, you will review the paper before the class, but you won't waste other people's time. You understand what I'm saying? Think about it that way. I mean, reading your paper is fine. If you don't understand, you waste your time. If you broadcast your misunderstanding to the entire class if it's trying to fall asleep, then they at least they picked up on their sleep or you wasted their time. They actually don't understand. So I try not to waste your time by letting you present, unless I know for sure that you don't. Since my PhD students, I know what they were back, and I will have. Why would they do it? Because I have. So that's okay. Yeah. So it's closest to presentation, except you don't have to waste other people. I won't allow you to waste other people. You will read, you will write reviews, but somebody else, the person who actually read the work presents. Okay, that's what I have. Readings from a variety of sources, including synthesis lecture books that I'm going to show in the next slide, as well as several shared articles. Okay. Those are the books. These are free. Okay. So it turns out these are the synthesis lecture notes. This is a concise introduction to models and methods for automated planning. Like I said, this is not the thing that you do to complete one course requirement. There are better things to do in life than do this course if you just want to pick something. Yeah. So concise introduction to models and methods of automated planning. It is somebody writing operator-based planning in a small enough book. There is much bigger textbook, but this is a reasonable textbook. Introduction to planning domain definition language. It's like PDL is a way of representing operators that we will use. If you wanted to learn, basically this book actually talks about that language, but you can use this book to get the full syntax. It's like a language syntax. Planning with mark codation processes is MDPs. Okay. Introduction to symbolic plan and goal recognition is essentially plan recognition, and goal recognition is the one where you are learning the user preferences as against the world model. Okay, so there is actually this, this one, I would think that this one we will kind of probably look at 30% of this book. This one maybe we'll just look at like 10% maybe. This one maybe another 10%. These percentages may add up to more than 100. I don't know. This would probably will get 10%. This one, we wrote this book, so maybe 300%. And then algorithms for reinforcement learning, that is Java, etc. Okay, so those are the books. I mean, they're all free. I'm not even making you buy anything. I'll tell you that you get them from library, just you can download them from library. Okay, mine you should pay directly, better than the publisher, but it's okay. So that's basically the books per se, and then the papers would be given to you before. Okay, grading criteria. This is what I said that I basically to be decided. I want to see what happens next Friday. I'm still hoping that some of you will say there is more things to do in life, and then go back to your interview. Okay. So I'll have few people and who are really interested. If you are really interested, it's okay. If it's a large class, I'll still be meeting. If it naturally becomes a small class, I'm not requiring it. I'll just see it. Then I can do different kinds of, grading things. So I'm going to decide that by next week because I think on Wednesday I will know because that's an ad block. Okay, that's basically the scenario. It will be a mix of project exams and paper reviews, etc. But I think more of certain kinds of things can be done easier if there is your people versus large scale. I think we already have by AC standard, we still have a reasonably somewhat smaller class. Then can do much worse. I think the last I checked it was 69 or something. It may have fallen after the break. I don't know. But we'll see. This I want to mention. We are going to experiment with slides. The bunch of stuff I said today, if you look at the slides, it's like, dry point, but actually a lot that has been said, and it's like really understanding what happened, even to actually read that again. There's no place. I didn't read right this. I just told you what happened in all the time. So I'm going to try this until it fails. I'm going to have 2 slides designated. I know that those of you like probably I used to say, lecture notes and we'll put, and some people will do it, some people won't. Mostly a couple of people do it, and the rest will just wait to see what they will do. But what I'm going to do this time is I'm going to have designated slides. Once again, I have the same philosophy. I don't want people to waste other people's time. Just the reason why I don't let you present, because unless I trust your judgment, I won't let you take striding unless I trust your judgment. Okay. So my hope is that PhD students are probably affected. Okay. So I'm going to have 1 PhD student for each class designated and 1 non-PhD student. I have to say that I like the people who have survived fall 2021 AI class. I think of them as like PhD. So if they want to do it, I would hope that they want to. But I know that they have many other courses, so if you don't want to do it, that's but in general, that's what we're going to try. You might be thinking, what happened to today's class? Dennis and Matthew, who unfortunately passed my office when I was thinking of this idea, you do it. So they are doing it for me. Planning. Okay. So they will do this and we'll see how that goes. So that's a good way of doing it. But I actually want it not to be directly declined here. So I think those 2, whoever are the 2 people, I mean, they are going to hopefully set a standard. No pressure, but so it should be some kind of a Google Doc or something, and then that both of you can edit, and then it should be wiki so that random people can edit. But you 2 can edit, and then if they read only version or a commentable version, that will put a link to it on that web. Okay. Expectations game. Serious time commitment for the course, active participation in reading, attending Piazza discussions. Piazza is like a whole entire lifestyle. Oh, it did change? Oh. Now it again. No, why is it not going? Oh, I can see. Oh, yeah, now, okay. This is funny. It's kind of going one behind. crazy. What I'm seeing here and what I'm seeing there are different. But that's okay. So that's what expectation game is. Serious time commitment. This only happened now, right? Yeah.
You like right on.
Like the last line.
Oh, okay. No, but this one is crazy because this one I do a clear version of next slide and it shows the previous slide on these two places. I have no idea. I would like a symbolic interface about that. But anyway, discussions are important, and then people actually, I mean, again, those people who have taken the class with me last fall, they know yes, is a lifestyle. And so, and I would keep that in mind as to how people are done. I mean, in an undergraduate course, I may not have given as much of a benefit to people who did lot more active discussion and active citizens. I will do it. There's no such thing as how do I just tick the pointers, because there's like a lot more you can learn, a lot less you can learn. That's, and then what you can expect, as I said, from the course itself, background on the current state of the art and all the stuff that I discussed, ability to read, understand, critique, some of the latest research papers, not necessarily present because I won't let you most of you present, and then ability to formulate and attempt to solve research problems. Maybe that I'm not again going to check, but you might learn that because you go to learn. This was supposed to be the break. As you can see, I'm very bad at assessing. But anyway, this is the current class makeup. The last I did, it has 69 11 are PhD students, 9 are bachelor students. All the bachelor students, I think, except one person, has taken that incredibly high path. The remaining are students. The one in the light blue are the morning numbers. The white are later in the morning numbers. So 27 MS in computer science, now the MS in the work systems. Yes. As I said already, and I don't want to be more, MS students to be carefully about that. I want to be useful. Okay. It's actually one of the very interesting points I should mention is, like I said, certain kinds of immediate reward wash over. But learning what your preferences are is self-discovery process. Everybody tells me the same thing. I mean, I've been in this game for long enough time that everybody will come to basically say, no, I'm going to do research, and I really do very research-oriented courses, whether they're doing masters or not. But then, you actually have to ask yourself what your true reward is. And if it's not, don't waste it. That's my point. So you should learn it yourself. Okay, that's a bit. Moving on. So I'm going to just mention unless you have questions. I'm going to wait for a second. See if you have questions. And then the first topic, it was supposed to be the second half. It's going to be operated. Yes. Please. What? Okay. Oh, the humans, the show. Oh my God, no. So we are now talking about my reviews of Netflix movies and Amazon movies. No, humans is different, I mean, Blade Runner, actually, the thing that's interesting about Blade Runner, I use it in my class, is how many of you have seen Blade Runner? Okay, so one interesting thing about Blade Runner is if you see the original Blade Runner, they were thinking of a futuristic society where there are planes flying between buildings, like micro aerial vehicles. Right between, as somebody said, they said flying cars, and I got 132 characters or 280 characters. Right. So people thought that was possible, in the original Blade Runner. That's the people who imagined that. The interesting thing is, remember what the phones looked like in Blade Runner. Remember how the TVs looked like in Blade Runner. I'll go back and see them. Bricks. You know what I'm saying?
The point is, the world evolves in all directions at the damn same time. You may be able to guess one line of evolution, but you don't understand how the different levels of evolution are affecting them. So in fact, the reason AI is working now has nothing to do with AI. Because the main ideas were there for a long time. I mean, the kind of AI systems are working, the massive systems are working, had things to do with internet, web, cell phones, with which people can take their cat pictures and upload it. None of this is AI. And yet that actually provided the infrastructure that allowed you to learn from massive amounts of it. That's my lesson for Blade Runner. But Blade Runner is quite different. I mean, I think humans, as I remember. But I particularly like this specific part. But I think there are more connections between Blade Runner and some parts of Let's Go, which is since sort of suddenly starting to have. It's like Lambda, for example. So, other questions? Okay, 15 minutes. We'll see what we can do. Okay, so we'll start this and then I'll get to read before we continue the discussion next time. So operator-based planning, the big picture again, like synthesizing go-directed behavior. Planning involves action selection, action sequencing, and also handling resource constraints. That part would be considered scheduling. Depending on the problem, plans can be action sequences or policies. The interesting thing is this was the intro slide in 2008. Wouldn't you have liked to be around that time? And you would have just done operator planning and you have been done. Okay. So I'm just doing because that was more or less for the operator planning. Domain independent or domain specific was the domain customized. We kind of understand this. You can read this, but in particular, we will give operators explicitly that will be domain independent planning. If they are sort of compiled into the planner, then it becomes domain specific planning. Okay. Yes. Really? Oh, very good. Okay, so what we're going to do, thanks for telling me. Actually, I forgot. I'm already in a zone and I'm zombied out. That I could have gone some random way until 10:30 or something. But the point is, we'll be talking. I'm going to show you the kinds of things we talked about. Transition systems and talk about operators of this kind and how those sequence operators can be sequenced together with general plans. We'll talk about blockchain, which is like a simplified word. We'll talk about the kinds of ways in which the planning can be done, state space, what's population planning, integration planning, and plan-based planning. Those are the things that we are likely to do. Okay, and I'll give you the readings from the Thank you, and thanks for finding it. What?
Nice. Oh yeah, I started off absolutely stoked for this class. Now this might be the only class I can have. Statistical, but that unimportant in the grand scheme.